All right, welcome to the Explainer. Today we're going to break down something that is, quite literally, the foundation of all science, physical measurement. And trust me, it's about way more than just numbers and rulers. It's about how we go from a simple guess to a scientific guarantee. So let's just dive right in with a little thought experiment. Imagine you're standing in front of a massive skyscraper. How would you figure out how tall it is if you couldn't just, use a giant measuring tape? Where would you even start? Well, the answer, believe it or not, starts with a tool you use every single day, probably without even thinking about it. It's the educated guess. In physics, we call it estimation. Now, the key word there is educated. This isn't just a wild shot in the dark. It's a real logical process. It's about taking things you already know from your own experience, applying a little bit of common sense reasoning, and coming up with a pretty decent starting point. So let's go back to our building problem. Instead of trying to guess the height of the whole thing at once, you just break it down into smaller chunks. You could look at one floor and think, okay, how tall is that? Maybe about 10 feet? Then you count the floors, multiply, and boom, you've got a solid estimate. Okay, so now we have a number. Great. But a number all by itself is kind of useless, right? We need to know what that number means. We need a universal language to describe what we're actually measuring. And that language is built on this idea of dimension. A dimension isn't a specific unit, like a meter or a kilogram. It's the fundamental idea behind the number. It's kind of like the basic grammar of physics, telling us if we're dealing with a length or a mass or time. And here's the really cool part. Just about everything we can possibly measure in the universe is built from just a handful of these fundamental dimensions. They're like the primary colors of physics. You can mix them together to describe basically anything. So how does that work for something more complicated? I mean, how would you describe, say, force using just those simple building blocks? We all kind of know what force is, but what is it really? Well, we can actually figure it out. We just start with that formula we all learned in school. Force equals mass times acceleration. Then we can break down acceleration even further. It's really just a length or a distance divided by time squared. So now we just swap in the dimension for each piece. M for mass, L for length, and T for time. And just like that, you've derived the dimension of force. Okay, so that's the theory, and it's all very clean and perfect. But applying this to the real world, that's a whole different story. Because in the real world, measurements are never perfect. And that brings us to two incredibly important ideas. And honestly, this target analogy is the absolute best way to get it. Look at the target on the left. All the shots are clustered tightly together, right in the bullseye. That's the dream, right? That's both precise and accurate. Now check out the one on the right. The shots are still in a nice, tight group, so that's precise, but they've completely missed the center. Not accurate at all. So let's break that down. Precision is all about consistency. Are your results repeatable? Do you get the same answer over and over? Accuracy, on the other hand, is about correctness. Is your result the true value? Think about it. A factory could have a machine that's incredibly precise, making thousands of parts that are all the exact same size. But if that machine isn't accurate, every single one of those parts will be the wrong size. Or think about that bathroom scale that always says you're 5 pounds heavier than you really are. It's very precise. It gives you the same wrong number every time you step on it, but it's definitely not accurate. What you want is a scale that's both, giving you numbers that are not only consistent, but also centered on your correct weight. And this whole quest for perfect accuracy and precision leads us to a fundamental and really honest truth about science. And it's this: no measurement is ever perfect. Every single one has a little bit of doubt built into it. We call this uncertainty, and it's super important to understand this is not a mistake or an error, like you failed a test. It's a necessary part of the process. It's how scientists say, hey, this is our best shot, and we're pretty darn confident the true answer is somewhere inside this little window. This honesty is what makes science so reliable. And this little bit of doubt can creep in from anywhere. Maybe the tool you're using isn't perfect, or maybe your reaction time with a stopwatch isn't always the same. It could even be tiny, random changes in the air that you can't see or control. So when you see a number written like this, with that little plus or minus symbol, don't think it's a sign of bad science. It's the exact opposite. It's a badge of scientific honor. It's a scientist being completely upfront and saying, look, we measure 20.5, but the actual value is almost certainly between 20.4 and 20.6 centimeters. But this raises a huge question, doesn't it? If every single number we measure has this fuzzy cloud of doubt around it, how on earth do we build bridges that don't fall down or send rockets to Mars? How can we calculate anything and trust the result? Well, thankfully, there's a whole toolkit for this. Physicists have clear rules for handling uncertainty. The first one is for simple stuff, like adding and subtracting. And the rule is simple. When you combine measurements, their doubts add up. You just add the absolute uncertainties together. So if you're adding these two lengths, you add the main numbers, 24 and 30, to get 54. But you also have to add their uncertainties. 0.1 plus 0.1 gives you 0.2. So your final answer is actually a little bit more uncertain than the individual pieces you started with. Now, when you get to more complex stuff like multiplication or division, say you're trying to find the area of a room, the rule changes a little bit. Here, you add the percentage uncertainties. It's a different method, but the core principle is exactly the same. Combining measurements always increases the total uncertainty, and that's something engineers have to plan for in every single blueprint they make. Which brings us to one last, pretty deep question to think about. If every single measurement has this built-in uncertainty, from the tiniest atom to the biggest galaxy, can we ever truly know the exact value of anything? Please tell your opinion in the comment section, and like and share the video with those people whose exams are nearby. Also subscribe to The Animated Scholar.